Hello and welcome to the second part of homework for part two. In this second half of part two, what we're going to do is take what we learned in the first half of this homework and basically take our feedback control loop and create a step response for it to see our change in H2, the height in the second tank. We can do this now because we have our transfer function for our process under feedback control. So at the end of our last video, the first part of homework 4 part 2, we were able to calculate our transfer function for our feedback control loop. So I'm going to call this TF underscore FB for our transfer function under feedback control. So now what we're going to do is do this step response and then plot how our height in the second tank changes with time. So if I go something like TF underscore FB dot step and then open and close parentheses, this will do a step response of 1 for our system. And if I press shift enter here, what we see is that these are the time values here, so 0 down to 142. And then this here is our step response from 0 to 1 basically. So let's see here. Let's go ahead, and what I'm going to do is go ahead and create some plotting points here. So I'll go tplot, or actually we'll go ahead and unpack this first. So I'll label these as our time points, and then secondly label those as H2. Now this is important to note here that these are all relative to the initial steady state that we were at. So this is just the step change from where we were at to where we've gone. So let me go ahead and make some plotting points here. So I'll linearly space out some points, linspace. We'll go np.linspace, and we'll go from 0 to 100 and do 500 points. And then what we'll do for our step change, we'll have t in terms of our tplot points. Okay? And now what we'll do is we can go ahead and plot this out. So I'll go fig is equal to make subplots. And we'll add a scatter plot, so fig.add scatter. Our x points will be our linearly spaced out points, tplot, and then our y will look at our h2 values relative to our initial values, so h2. And let's plot this out here. And you see here, what I've gone ahead and done is when I was practicing this out before, I had already changed our integral control here to 0.8. But what we originally had it at was 10. And what we can see when we run this is that when we do our step change and we have our integral control at 10 here, we go from our initial steady state in our process, and we go up some, and then we, after some time, looks like around 50 or 60, we start getting to our full 1 step change that we had requested of the system. But what we are asked to do here is like I had it before, is go back and change our integral control down to 0.8. Oops. And what we find here is that our system becomes unstable here. So it shoots over our step change set point, so up to almost 1.8, and then oscillates for a while, and eventually gets down. It's still oscillating a little bit, but over time it gets down to our set point. A step change of 1. So obviously this is not what we want if we were to do a step change and we only wanted a step change of 1. But basically what we have here, we can also go ahead and raise our gain here, our KC, and you can see the oscillations essentially get worse. So if we lower our gain here, obviously that will make our oscillations a little bit more dampened. But we're still unstable here. So essentially what we have here is we are inputting a step change, but what we are getting is some oscillations if we were to lower our integral control down to 0.8. Okay, so now what we're asked to do is supply a sinusoidal cosine error input to our forward transfer function, and just to see what the response is after it has passed through our forward transfer function. So what I'm going to do here is there's something in SciPy Signal called LSIM, and essentially we can give it a transfer function and the input, and it will at a time period, and it will supply us what the outputs are from that system. So what I'm first going to do here is we're going to want to basically plot what our output is of this sinusoidal cosine input, and also compare that to the input to see how maybe the amplitude has changed after it has gone through our forward transfer function. So I'm going to create some plotting points here first. I'm just going to call them tsim, and I'm going to linearly space them out. So np.linspace. We will go 0 to 50, and then I'm just going to do 1,000 points. And then what we need to do here first is create that cosine input to our transfer function. So I'm going to call it E for error, and because remember we have our feedback control loop, and what it's going to be is np.cosine, and then because it's a cosine curve, what we're going to need to have is some frequency, W, and then we're multiplying that by our times here. So I'm just going to go ahead and specify that frequency. We're going to use 1 radian per second. So W is equal to 1. And now what we can do is go ahead and use that LSIM to be able to supply our transfer function and our input to be able to get the output that we're looking to plot here. So if I go sig, I believe I imported SciPy Signal as sig. So sig dot LSIM. First we'll have our transfer function that we want to input here. So we'll do our forward transfer function, which I believe is TF lowercase f. Yeah, lowercase f for our forward transfer function. We have our input here, which is our cosine input. And then we have our timestamp here at the end, so tsim. And if we run this, what this outputs, it outputs 3 different sets of numbers. However, what we're looking for is this second set of numbers here. That is our output. So what we can do here, there's a lot of numbers. But what we can do here is we can just grab that second set of numbers as our output, H2. So I'm just going to go underscore, comma, H2 for that second set of values. And then for our third set, just call it underscore again. So now we have been able to grab the output, our heights. So what we can do now is we can go ahead and plot that input, cosine error input, and also compare that against our output here, H2, to see if that those cosine waves have changed in amplitude, and if so, how much after they have passed through our forward transfer function. So I'm going to go fig. Well, actually, I can just copy and paste here. Let's see here. I'm going to change this to tsim. I'm going to give this a copy and paste to superimpose our input. Our input is E, and let's go ahead and plot this out. Okay, let me go ahead and give these a couple names here, just so we know what we're looking at. So I'll name this, this is our H2, so this is our output. Oops. Output. And then this is our error cosine input. So name is equal to input. Oops. Okay. So you notice what happens here is that our the amplitude of the output, it's originally a little bit high, but then when it comes down, it is actually lower than the amplitude of the input. Now, what is also interesting is that basically the peaks of these curves are completely flipped. They're at a 180-degree angle. And this makes sense because if you look back at our control loop, we have our cosine input, our error input to our transfer function, and then it goes back around through our backwards transfer function, and then goes back to our comparator. And when it goes into that comparator, we're basically comparing it to our original set point. And what that does is it flips it because of that subtraction. So that's why we have the difference in peaks here between our input and our output. But another thing to note here, you notice that we have our gain here, Kc equal to 1. And it looks like we get, we eventually reach we get stable here towards the end of our time span. But if we go something like raise our gain, basically double it, so we're not as stable, at least as far as we can see here. And when we go and run this, what we see, because we have raised our gain so much, our output amplitude has been essentially, because of the overcorrection, the output amplitude is a little bit higher than compared to the input amplitude. Notice that we still have almost a 180-degree difference, that phase lag between our output and our input waves. So this will do it for homework for part 2. We'll talk a little bit more about this last part that we did in part C, but that will do it for part 2. Thank you for watching.